Okay, so now for the approximation of the wave equation. So here are approximations for first derivative and second derivative. And remember that the wave equation is like the heat equation in that it's got a length and time. And we want to know what's the position of a string, right? If we know its initial position and its initial velocity. So for the heat equation, if we want to know the heat one time step in the future, we just needed to know these 3 points. But for the wave equation, we're actually going to need to know also that one. And that's because the wave equation is second derivative in both t and x. So u of ij plus 1, that's the position of the string, right? That's vibrating one time step in the future. And we want to know how that depends on its position now. If we think of time j as now, its position now and its position one step to the left and right, and also one position back in time. So we have boundary conditions, which are actually pretty simple. The boundary is fixed, it's 0. The position doesn't move. But we also have 2 sets of initial conditions, unlike the heat equation. We have initial position, which we usually call f of x, and we have initial velocity, which is g of x. And the equation we want to do for the wave equation is utt equals c squared uxx. That's going to be our, that's the wave equation. Okay, so what is the wave equation? Well, we need to use this formula twice, once on time and once on position. So utt is going to be u of, let's see, I j plus 1 minus 2 uij plus uij minus 1 all over delta t squared. So that's saying that utt involves this, this, and this. And that should be equal to c squared times u I plus 1 j minus 2 u I j plus u I minus 1 comma j all over delta x squared. So uxx depends on these 3 points here. And we want to know what's the position at that point, which means we want to solve this equation for that thing there. So that's actually not hard to do because we just, move everything around. So uij plus 1 is going to be equal to c squared delta t squared, multiply both sides by delta t squared over delta x squared, times the numerator on the right side, ui plus 1 comma j minus 2 uij plus ui minus 1 comma j plus 2 uij, because we have to bring this over, and then minus uij minus 1. And those come over from the left side. So calling this, like we did for the heat equation, we'll call this S. That gives me uij plus 1 equals S times this term, which is ui plus 1 comma j, plus this term, which is ui minus 1 comma j, plus, well, we've got a 2 uij there and a minus 2s uij there. So that's 2 times 1 minus s uij minus uij minus 1. So there it is. There's our update formula for the wave equation. We have to deal with initial position. which isn't too bad. Initial position is at j equals 0. So I0 equals our initial position function, just evaluated at f of I delta x. Initial velocity is a little bit trickier. Again, we're dealing with j equals 0, but it's u sub t of x comma 0 equals j of x. We have to deal with this derivative at somehow. So what we'll do is we'll do an alternative first derivative approximation. We know that the limit as delta t goes to 0 of some function h of t plus delta t minus h of t all over delta t equals h prime of t, right? And we're comfortable with that because that's just the basic idea of a derivative. If I've got some function and I take some time point t and another time point t plus delta t, find the slope of that, and we let delta t go to 0, and we find the limit. Well, we can also do this as limit as delta t goes to 0 of h of t plus delta t minus h of t minus delta t over 2 delta t. It's the same limit, but instead of, if we want the derivative at that point, what we're going to do is go out to t plus delta t as t, and we'll go out to t minus delta t. We'll take the slope of this line, and keep in mind that this distance here is 2 delta t, which is why we've got that in the denominator. And then we take the limit as delta t goes to 0, which means we're taking the limits of these secant lines, and that'll give us the tangent line. So for delta t small, h prime of t equals roughly h of t plus delta t minus h of t minus delta t all over 2 delta t. Now we want to apply this to u sub t. So that tells us that u sub t at I delta x with time equal to 0 is roughly u at the point I delta x times 0 plus delta t, that's this part, minus u at I delta x, 0 minus delta t, that's this part, all over 2 delta t. Now this left-hand side here, this is our initial velocity g at I delta x. And this term is u sub I, but time step forward 1. So this is u sub I at time 1 minus u sub I at time minus 1 over 2 delta t. Now, technically, the u sub I minus 1 doesn't actually exist because we don't have any time before time equals 0, but it's a useful fiction for now. That's actually called a ghost point, and we will eliminate it in a second, but it's a useful thing to have right now. So equation 1, ui comma 1 minus ui comma minus 1 is equal to 2 delta t g I delta x. Equation 2 is this one, and that's just looking at the update equation with j equal to 0, and you get ui 1 on the left plus ui minus 1 is equal to s let's see, s ui plus 1 comma 0 plus ui minus 1 comma 0. And then the rest of the update formula is 2 1 minus s uij by 2. So this is update formulas j equals 0. And why we like that is because now we've got two equations with a minus and a plus on our ui minus 1s. And so ui comma 1 is we add these two equations 1 and 2 together and divide by 2. So it'll be ui comma 1. That's my, oh, right. So it'll be 2 delta t g I delta x plus s ui plus 1 comma 0 plus ui minus 1 comma 0 plus 2 1 minus s ui comma 0. I feel like I'm forgetting something. Okay, I wasn't actually missing anything. So let's keep in mind that this is my initial position at delta x. That is my initial position at I minus 1 delta x. And this is my initial position at f of I delta x. And so that gives me my wave equation. So this is the update. The initial position is this. This is time t equals 0. This is time t equals 1, is this down here. So we've got t equals 0 and t equals 1 set up. And then once we know those two, we can just calculate all the t's going forward. So I'm going to switch the share to look at the wave equation. So here's the wave equation. C is 1, you can change that. Delta x is 1, delta t is 0.1, s is 0.001. Yellow background here, this is my initial velocity. I set it all up to 0. The green background, that's initial position. So we've got something that is a string that's up here, and then 0 there, and then down. So that's my initial conditions. This orange part is that first time step that takes into account the initial velocity. And then we just do the update over and over again. So this is pretty much like the heat equation as far as the mechanics for Excel works. And there's a view of our wave equation. You can see that it's periodic. And it repeats itself. Any cross section of this will give you the shape of the string at any particular time. So time is going forward. And of course, you can tinker with this. You can change the s's. You can change delta x, delta t. You can change the initial velocity, the initial position, and it'll update itself automatically. So that's the wave equation discretized.